environmental and engineering applications. So Professor Cherif Ould-Lahoucine is full professor from Mechanical Engineer Department from Guelma University in Algeria, and Professor has more than 30 years of experience in teaching and in scientific research. And the focus of your research is about renewable energy and heat transfer. And please, Professor, complete your presentation. Okay. So thank you for coming and thank you for your ability to give this seminar for us.
So I first would like to thank all of you who accept to attend my today's presentation. So after coming here, Professor Video asked me to make a presentation about maybe the topics that are, let's say, close to my interest. Of course, in this presentation, not every research I did before is there, but I picked some of them that could be of interest to maybe some of you, right? So the title is Heat Transfer at Different Scales. So this is the half of the title of the presentation. Different scales is something important in heat transfer. The scales, each scale has its specific conditions. When you shift from one scale to the other one, something changed. And we have to take or to pay attention to this aspect of scales. But from my small experience in research, I find it very, how to say, very fruitful to have made the research in different topics. And after years, with the experience, you will find that you need, for example, the information you get it from your research, for example, in macro scale, in micro scale, and even in nanoscales. That's why you will see that I will start with a topic in heat transfer. It's a very complicated topic, by the way. It's boiling heat transfer. In that topic, I will try to show you, even maybe if probably some of you doesn't really have a clear idea about this phenomena, but I will try to do my best to make it as simple as possible to explain why different scales are there. So you cannot tackle or find solution to this problem if you just based your thinking, equations, and everything on a single scale. So that makes this topic very, very complicated. And after that, I will show you also that once I started to be interested in such, for example, kind of problems, I shifted to something which is related to the nanostructures. And the nanostructures, I went there to determine thermal conductivity of these nanostructures. And because, as I said, when you are looking for different scales, there are new properties specific to that scale. And at that time, I was not that young. I mean, it's about 40 years old at that time. But I was forced, even as an assistant professor, to start learning, how to say, physics, solid physics. And my background is coming from engineering. So if I can allow myself to give advice to young generation, sometimes don't think just to focus only. You said, I'm from that background, I have to learn only lectures or topics from that background, but this background is beyond my interest. Be careful about it. Science is not a black box. If you are not, like Feynman said, there are plenty of rooms at the bottom. If you are not able to open other doors, you will just understand the topic, let's say, theory. But this is not an assurance that you will find solution. So that's at the beginning of my presentation, right? So it's kind of advice. So the presentation plan will be like this. So I said at the beginning, I will try to give an example of a complicated heat transfer phenomenon called burning. Then from that presentation, you will catch that the length scales in heat transfer is very important. The examples of fundamental research topics. So I try to make, how to say, my presentation by showing two aspects of research. Fundamental one, and the engineering one, number 4, some project engineering. So as researchers, of course, I was interested in some fundamental research. But in the same time, I try to give something I learned from my experience outside the countries, because I graduated from Japan, and also I did research in the United States of America, Georgia Tech, and I went also to France, Italy, and so on. So from that, I have to give something back to my country, because my country is facing, of course, some challenges in engineering, how to develop our economy and so on. So if I can contribute with my modest experience, that would be good. That's why I tried also to work on some engineering applied topics. And I finish with some conclusion. So that's happened to me. After I finished the PhD, there is a question. What I have to do now? Of course, your supervisor decides the topic for you, but once you finish, you have to find your own way. And it's not always easy to find that. You said, I will do that, I will continue on the PhD topics. Maybe there is something that everyone is working on that, etc., etc. Therefore, I find myself in front of different doors, and I have to decide which doors I have to do. So, the boiling process. The boiling process is one of the most, of course, effective heat transfer modes that is capable of transferring large amounts of heat. And the main advantage is you can make this heat transfer with a very small temperature difference, which is not the case for the other mode of heat transfer. I will show you in the next slide what I mean by that. So, within the boiling heat transfer, there is what we call nucleate pool boiling. This has wide range of application. For example, cooling of nuclear reactors, evaporators, thermal desalinations, chemical industries, and even the cooling of microelectronic chips, right? So that's an example. So if we look to this figure, we can see that the heat transfer coefficient, so just this one, right, is different depending on the nature of the heat transfer. This is natural convection, this is forced convection, and this is boiling. So if you compare, you will find that heat transfer coefficient is different from one medium to the other. For example, air is the lowest one. It's not very good. Actually, we use air generally for thermal insulation because of that. This is fluorochemical liquids. We use it actually for the cooling of electronic chips because we cannot use water. You imagine water in the computers? This is catastrophic. And this is water, which is a medium that we use so much, okay, in the experiment and find several applications and so on. This is for natural convection. You see that the coefficient is so low. The maximum is for water, it's about 0.1, so watt per centimeter square Kelvin. But when we pass to the forced convection, which is forced convection, means this medium, you use kind of pump, for example, for liquids, or fan for gas or whatever, and you create a movement to the fluid to increase the heat transfer coefficient. You can do that, but you reach a maximum of 10, right? But imagine you are in bowling, 1,000. So no way to compare between this mode of heat transfer. Bowling is by far, but bowling has a problem. Yes, this is pictures of nuclear bowling. Look, there are some kind of difference between that. In that first pictures, we can see that the bubbles have a different, how to say, diameters, if we can consider this as spherical. But in critical heat flux, that means when the heat transfer or the heat flux is increasing, these bubbles becomes larger and make coalescence. And after that, we obtain what we call a film bowling. So this is very dangerous for nuclear reactor. I know this because I graduated Ph.D. in nuclear engineering in Japan. Okay, so we know this topic. If this happens, it's kind of greenhouse effect. The heat you want to remove to cool the nuclear reactor is not removing. So the contrary happens, the melting of the reactor. This is catastrophic. Therefore, we need, because it's a huge amount of heat transfer in nuclear reactors, we need a very high heat transfer to remove the maximum of heat. And we create from that, after that, you know, if you have thermodynamic advanced courses, so we can use this to generate the vapor, then electricity, and so on. So we need a high heat transfer coefficient, but we should be very careful about the problem of film bowling. So we need to work as much as possible in this area, nuclear bowling. We get high heat transfer coefficient and avoiding in the same time the problem of this film bowling. So that's an example of the heat transfer by bowling. Then, in overall, so I tried to simplify the problem, I said the bowling offers two key advantages over if we compare to other cooling configuration and technologies. The first, as I said, because the heat transfer is so high, we greatly reduce the surface temperature. So cooling is very effective. It's perfect. Okay. Next is, this is very important, is fairly, I said fairly constant surface temperature during the large refrigeration device. Next slide will explain what I want to say. Look to that. This is actually the region of natural convection. Look, your heat transfer coefficient here is about 8 maximum. Look, difference in temperature is about 80. Wow, it should be. Forced convection, you are here, right? So your forced convection, look, here, in this region of nuclear bowling, look, this. The slope is so important. What it means? It means that your temperature difference is too small But heat transfer is increasing so much in this area. So that's why we are interested here. Nucleate bowling, temperature difference between the temperature of, I will explain to the plate and the fluid you are using for cooling, right? So it's about very small. For example, this is, with bowling, you have 70 degrees. Without bowling, 525. So for sure, you have melting of your nuclear reactors. So that's to show the merit of bowling. Now, I arrive to something which is the main, one of the main, how to say, points that I would like to stress during this presentation. The scales in bowling. Bowling is like this, right? No problem. Look. So you have bubbles. These bubbles have different dimensions. So here, the scale is about centimeters or millimeters. It depends, right? So if you want to make a model for that, you need macro scale heat transfer. Continuous medium. You have to know that. Fluid mechanics, heat transfer, and so on. Then, in the modeling, you have to consider also each bubble by itself. So you focus on each bubble. This is the scale. So that's what happened. There is some what we call the dry spot. I will not go so much in details about heat transfer, just to explain to you that if you want to model this problem of bowling, it's something mandatory that you need to know that you have different scales, not only one. So macro scales is here, should be. If you are using any day morning with professor, we had very interesting talking about this kind of research about bowling, because he knows bowling also very well. So he said that we try to give to the student the opportunity to make simulation using, for example, advanced softwares. So these softwares use this kind of research. You can find this. Fluent can do that. Macro scales, continuous medium. Here is different. You are in, let's say, in a scale that need macro and micro. Here, if you focus more on this area, look what happened. This dry spot is there, and the thickness of this is very small. It's about maybe less than 1 micrometer. And why I have to focus on this? Because the creation, the growth of these bubbles come from this region. Heat transfer in that area is by conduction. Evaporation from the top. And water is coming. For example, here, there is evaporation and water will come to fill the gap. So, the modeling, if you want to model the bowling heat transfer, you need to know macro scale heat transfer, two-phase flow, because this is vapor and this is liquids. You have to know what happened as a mechanism under the bubble, and I'm coming to say that this topic is about a century. Everybody, there are several researchers that are doing their best to propose what we call a correlation of the problem. What is the meaning of correlation? Correlation is an equation that you can use it to make prediction, but however, be careful, this correlation is valid only under a specific condition of that experiment. I have to stress this point. If you are trying other experiments in different, for example, conditions, this correlation cannot work. Or at least, it will not give as accurate result as for the case it has been developed. This is very important something. So here, what the maximum of the researchers thought is this micro layer is responsible of bowing. I'm using responsible. It doesn't mean this is 100% to explain the bowing. It means there are other phenomena, but maybe less important. Not maybe, for sure, according to them. For example, this conduction through the micro layer is responsible for 85% of heat transfer in bowing. And the remaining 15 is about different other topics. So what we did as researchers, we are not, for example, able to make a model that takes into account everything. That's impossible, because sometimes it's very complicated. However, if you make some assumptions, in order to reduce the complexity of the model, with the aim to obtain a model that can give you somehow accurate result, and you use it in engineering. This is the last aim, or the main goal for you, is to solve something in engineering. That's perfect. But you have to write this model, or this, how to say, simulation, etc., is valid under these conditions and can give accurate result for engineering application about, for example, 90% or 80% and so on, even 70%. Not explaining everything. That's what I mean. So that's the bowling. So we can see here there are different scales to take into account. Otherwise, it's difficult for you to exactly model this complicated phenomenon. Next. That's what happened. Look. So it's like the video that I showed up. Bubbles are different, how to say, dimensions and so on. So you have this plate. So this is macro scale or two-fluid model, because you have liquids and vapor. This is the heating surface, or the heated surface, very important because you need to tackle the problem of interface. How these liquids behave in presence of, for example, a plate in copper. It's not the same with aluminum. That makes this topic very complicated. And I will show you after that other things. So if I take one single bubble from this bubble, for example, it behaves on the plate. You have this small groove. And this is responsible of the nucleus, like a baby. Nucleus, then baby, then a man, etc. Development. And after we pass away, like the bubble will rise and then disappear. So this is nature. We should start for something. So the observation in the experiment showed that this is very important. This morning we had a topic very interesting about this. Why it's important? It happened that depending on the angle and the depth of this bubble could develop, okay, and then detach. And this is very important for bowling, because once it detaches, that means it takes the heat to the outside. So it's working as cooling method. But imagine, it happened that for some kind of angle and depth, the bubble cannot detach. So we are going to this film boring, which is not good. So people are trying now with this nanotechnology. They said, okay, once we understand which angle is good, we will make our surface with microstructures with the optimal angle and the depth, in order that we create bowling and we have no problem of bubble remaining on the plate. That's perfect, they said. But it's not always that easy. This is theory, right? In practice, sometimes they get some good results, in others no. Next, So here, in that area, if you leave this, this is what we're talking about. This is the micro layer, and this small things looks like the atoms. Oh, I'm using a very complicated word. The atoms means nanoscale. Be careful. So here, the interaction between this plate and in this area, because the scale is different, the force of attraction between the plate and the atoms of that liquid is too strong. You cannot neglect it. So some forces are neglected. If the scale is large, that's what we call macro scale or continuum medium. But once you go down, some forces like tension force becomes very important, and you cannot neglect it, because from that forces you can understand what happened. And why this bubble is detaching and the other no? Gravity, you have to compare your gravity force, once it's detached, with the attraction force between the plate or the first layer of the atoms of that plate and the force atoms that are very close to that plate. And I was thinking about this when I used to be a student in Japan, talking with my prof, asking the questions, trying to answer. And then I said, before leaving Japan, I have to continue on that topic. And I'm pretty sure, I was young, you know, sometimes you have good ideas, sometimes no. I said, I'm pretty sure that if we tackle the problem with molecular dynamic simulation, I will get the result and can solve problems. I was not that humble at that time. I was thinking that by myself I can do something. But everybody was kind of blind, which is impossible. Anyway, I tried, and we will see what happened. So, this is the problem of bubbles. So, different scales. This is just to show you the scale of things that is in nature, okay, the DNA and so on, and for example, if you have also your hair, etc. And this is what the human created by looking to nature, this problem of microelectromechanical systems and so on. So we are trying to fabricate something at the micro, and the nanoscale is more complicated, but micro is okay. That's why we use microelectromechanical systems, because it finds some applications in different topics, medical and so on. So that scales exist in nature, and the human, in some advanced lab, they could even create or fabricate such a small scale. Next is, I return back to this bubble that stuck with me, so I cannot maybe be free from that bubble. So the bubble I return back, so here is, as I said, the bubble is created in that, or the nucleus, the first nucleus, has been created here. This is the plate, so the heating surface. And this is what happened, as I said, the thermal boundary layer, so the water, once it's evaporate, so water come here to fill the gap, because nature hates the void. That's what we learn, so it comes. After that, so this is the model. So if I want to model, that's what I was thinking. I said I have to focus on a single bubble, which is wrong, actually. Which is wrong if you think that you can tackle the problem only by modeling one single bubble. Right? This is important to understand, but it's not enough. So, the micro layer, etc. Good. So, bubbling, as I said, I return back, because it's created, or the first nucleus is created in a cavity which has a specific angle and depth. This is shown here. means that if we are using kind of microscope on the surface of the material, you will find it, as you know, something, how to say, very, it's not, nature is not perfect. I mean, in the way that you're looking at the surface, you feel that this one is perfect, but it's perfect because in your eyes, the capacity to look to a surface is limited. But if you go down, you find that there are many imperfections. And the idea is like this. If we want to model the bowing heat transfer, we have to consider everything, of course. Single bubble, yes, but the whole volume. So, my idea after I returned back from the United States is to use kind of statistics. What I mean by that? And in that way, actually, artificial intelligence could be interesting. Because from artificial intelligence, you can get information, for example, copper, surface, the distribution of these imperfections. Then you can get the range from that whole surface, you get the range of the angles that are responsible for the creation of bubbles. I don't know if you get my idea. Repeat again. If I look to this one by itself, for example, here, the angle, for example, is 30. 30 is good to create a bubble and to detach. Good. But imagine another imperfection here. Here, the bubble is created, but it cannot be detached from the surface because the angle is not like 30 or more than 30. Therefore, from that information, every angle equal and greater than 30 will give you the opportunity to create a bubble and to detach. Therefore, from the distribution, you can know exactly, on average, what could be your heat transfer using bowing heat transfer. Because the number of bubbles you can know, and their dimension, because after that you can go to the scale under that to model your bubble. That's what I mean. For example, if you focus on this, look, if you focus, you will find that here also with microscope there are other scratched surfaces, and then you can create your distribution, the cavity size range, which correspond to bubble nucleation. Means only in this range you have the number of bubbles that can be created on that surface and detached. The other none. So you can do some kind of model. Okay, so I went to United States of America looking to solve the problem of interface from single bubble. But the problem, once I start to learn by myself, molecular dynamics simulation, there are a lot of theory and so on. So the same problem as before. You have a plate, okay? You have your water, their atoms and so on. But if you look to that pictures, the dimension is very small one. That means you are doing simulation very small scale. But how about the bubbles we saw in reality, actual situation? It's not that small. So your supercomputer can give you information, more or less, about what happened at that scale, but not to solve the problem of bowing heat transfer, because the scales are different. So here, angstrom, 36, 7, no way. The other problem of molecular dynamic simulation is this. Look, what's this? These are the potential What is the potential? In order to make simulation with molecular dynamics simulation, you have to know the forces between the atoms of water and between water and the surface, for example, in copper. But the problems, maybe you have good lectures here about what happened in material science. You have to know the potential of that forces. And we learn only perfect potential, which is the Lennard-Jones. Wow. But what happened between water and copper, for example? What kind of potential? If you don't have potential, the forces is wrong. You are using in the simulation. So because the force is coming from the potential. So that's the weak points of molecular dynamic simulation. Simulation is just for very small scale. And the other problem, the output of that simulation is coming from a potential that you suppose is perfect. But in nature, we don't have only Lennard-Jones potential to determine the forces that you are using in molecular dynamic simulation. So after I start to learn this nanoscale heat transfer, I said, yeah, that's good. Maybe I have, because I returned back to Algeria, I don't have supercomputer. Even in America, we suffer. So in Georgia Tech, to get maybe a large, how to say, result from dynamic, molecular dynamic research. So imagine in my university, we don't have such capacity. Therefore, I have to adapt myself to the actual situation I'm living in the university. So I shift to thermal conductivity of nanostructures. Thermal conductivity of nanostructures, this is nanostructures, some pictures, okay? Nanotube and so on. And then there is some structures that has been created in the lab by Professor Wang, like millions of Chinese, Wang, but that Wang is in Georgia Tech. Actually, he was even shortlisted as Nobel laureate for physics. He created in the lab different structures with different geometry. This is called nanobelt, like a belt, you can see so here. So, and even ring, yeah, something. So, of course, he's only interested by creating such nanostructures, and after that, the other researchers try to determine their thermal, mechanical, electrical properties, and to look where in which field they can find applications. So for my case, I said, dynamic molecular simulation, I cannot use it to determine thermal conductivity of every nanostructures we deform. That's impossible. So I was thinking with one of my colleagues and friends in France, Professor Chantrel, to use what we call kinetic theory of gas, what we learned in thermodynamics. It looks very strange, so to use the kinetic theory of gas to solids. Anyway, so we try, and we do some simulation. This is an example of SNO2, so the tin dioxide of tin. Okay, this is physics, so I start learning now physics. Yeah, first Brillouin zone, this kind of, I'm coming from engineering background, so I start looking to books, maybe Kittel, all these kind of books, very famous for that, and it's not easy, you know, when you have 42 years old, but still, even with kids, everything, I try and try, so I understand the method, good. Then we did some, this is our publication journal heat transfer. So this is the method, so you have what we call Phonon energy density, and then from that energy, we can obtain the capacity, heat capacity, so this heat capacity, so it's the derivative of this Phonon energy density over temperature. So you look here, I'm very fundamental research, okay? Oh, sorry, just to show you something. Oh. So this is, then we can determine the thermal conductivity of the nanostructure using this equation. So in this equation, we have this heat capacity, this is the velocity of the group, depending on the, how to say, the mode, and the polarization. This is what we call the unclap and the impurity, etc. So the relaxation time, so it's very physics. So. And this is the angle between the group velocity and the structures. So this is distribution. Bose-Einstein, it's not actually Bose-Einstein, sorry. This is Planck distribution, okay? So this is capacity and the group velocity and so on. Then I obtained this example. So what we did, actually, I will explain to you. Once you have this model, you have to validate always. This is for everyone. If you are proposing any kind of model, this model, people should trust you. How they can trust? There are two possibilities. If you have this possibility and capacity to make measurement, that's perfect. You will compare your own experiment. Or you pick experiment from other guys. They have lab with equipment and so on. So at that scale is very difficult. We are talking about nanoscale, be careful, guys. So to find an experiment, even in America, believe me, it's very difficult to make thermal conductivity measurement of nanostructures. It's not easy. Therefore, the method is like this. It is supposed that if you can, you can determine thermal conductivity of the bulk, the big one, so you divide this, and you can obtain the small scale. So from that model, we go to bulk. And this, I think, this is thermal conductivity, which has been measured from authors, the name is Terps and all. And this is our calculated values. So we can see within this range of temperature, very low, and ambient temperature, the room temperature, the fitting is very good. That means the model is working. That means we did some kind of validation. After that, I can use this model to determine thermal conductivity of nanostructures. So what he did, so I will show you something interesting. That's picture. So there is one professor, is very famous, actually he graduated from Berkeley, University of Berkeley, Li Shi. Now he's of course Chinese. Maybe the name is easy to guess that he's Chinese. So Li Shi make measurement. Okay. So this is a measurement of Li Shi. For example, nanobelt of 64 nanometers, right? Yellow, the model proposed by Li Shi. Li Shi is using a Boltzmann equation. So it works. 64. Now, this is the model of Li Shi for 53 nanometers. So less thinner. And this is the measurement of Li Shi for 53. Wow, huge difference. This is our model for 53. Perfect. That means this method works very good for kind of specific nanostructure, not everything. For example, this, some very complicated shape, no. Okay. I have to make this very, so this is the physics. So we have, I don't know if you have such lectures before, what we call the first brewing zone. And from that brewing zone, we use some calculation to determine the wave vectors, and then we make the sum, etc., etc. Okay, so that's physics. I passed now to engineering. So I return back to Algeria, as I said, and we need to do some engineering project for our countries. One of them is the hybrid photovoltaic thermal PVT collector. So as you know, this system can give you simultaneously electricity and hot water, right? That's good. I mean, specifically in some remote areas, they don't have access to electricity. But in Algeria, of course, because we have natural gas, so electricity is almost everywhere. So no problem. But anyway, we can propose even this kind of system to some African countries, and they don't have anything. No way. So no electricity, no water. So the problem here, in hot countries, as you know, the photovoltaic panels, once the temperatures, the ambient temperature goes up, the efficiency is down. So that's a big problem. Therefore, people are always looking to make cooling of such system. Okay? So generally, as we see here, the water is under. It's under the PV, right? So the problem is not solved, because solar radiation is coming directly on the PV panels. Of course, you have hot water. This is probably good, maybe, for example, for Denmark or whatever, but not for Africa, right? So my idea, once I was looking to one article in Nature, in that article I saw that water is absorbing, it depends, of course, on the wavelength. Majority of the wavelength that water absorbs is in the, how to say, infrared. Infrared is the responsible of thermal energy. But the visible, no. It's kind of windows that allow the visible to pass. And visible is exactly the wavelength that photovoltaic is using. So for me, it's contrary. I have to put water on the top of the PV. So if I put water on the top, water will absorb infrared, hot water, and visible length will pass directly to the PV. So I protect my PV panel. So that's what we did. This is what I want to say. So, right? So this is the radiation, solar radiation, right? So we can see here, look, this is water spectral absorption. Look, it passes, but in that region of wavelength, it absorbs maximum. So thermal energy absorbed here, and visible will pass here. So this is perfect. Now I have to make a proof. So that's what I mean. This is water, solar concentrated, so pass. So we have the visible and the infrared together. Okay, so pass. So water will absorb infrared, hot water outside, but visible pass directly to the PV. Good solution for hot countries. So that's the system we propose. Okay, and this is an example. So here is a PVT that I showed you at the beginning. It means that water is under the PV. Look, at the beginning, this is temperature. It's cooling good. But once water is warming, at the end, it's very, very hot, about 126. So this panel could break. But present proposed be this one. Look, cool. We don't have this kind of spot on specific region, specifically at the end, because after it hot, warm, and then this is a problem. Sorry. That's an example, and interesting. So during this modeling, I find something very interesting. Look, in this system, actually, I didn't use the serpentine. I use a channel, because in order to cool the hard surface, I use the channel. But once you're using the channel, there is a height of such channel. So one question which is logic, which height I have to select? 1 centimeter, 2, 5, by chance? In fact, it's not like this. So the height of channel, look in centimeters, we can see that the energy efficiency change with the channel. Example, here. This is the energy efficiency. Energy efficiency is increasing when the channel is increasing. Means if you are using for example, the channel for the water to cool the 1 centimeters, your efficiency is about 65%. If your channel is 4 centimeters, your efficiency is almost 90%. Now, in energy, we have also something very important. We call this exergy. What is exergy? Exergy is a quality of energy. Energy has no same quality. I explain. Electricity is better. For example, today, if there is no electricity, no presentation, but if you bring with you, for example, hot water for me, you give me energy, but I have nothing to do with this hot water to make my presentation. So this is energy, and electricity is also energy, but internal quality is not the same. In PVT, because we need electricity from PV, we have to look to the exergy. So what happened? Sorry. What happened to this exergy? What happened to this also? To go back? Okay. I don't know. So in exergy, I have to return back. So what we notice in terms of quality, the quality is working exactly the contrary of the efficiency. Means if you increase the height of your channel, quality is reducing. So it's kind of competing effects. And here comes what we call optimization. We need quantity and we need quality in the same time. So competing effects means I have to find a model to determine the optimal channel height. And I succeeded in this. After that, okay, this is the problem with nanofluids. Everybody heard nanofluid, nanofluid. Nanofluid is increasing heat transfer. Nanofluid is perfect. Nanofluid. Okay. There are two main problems. Agglomeration. You know these kind of particles? They go down. So there is a problem with the PEMs. The other problems, in theory, nanostructures are distributed evenly around the whole volume, but in practice it's not that way. Okay. Myself, I proposed this nanofluid type, means this dioxide of titanium nanofluid, and we try to see if this is really improving heat transfer with the PVT. What we find at the end, this is different because this is an equation that I proposed even as a new equation to determine thermal conductivity of nanofluids. But what we find, this is the channel. That's what I'm trying to explain. Look, here is the exergy, means the quality of energy in red, unique, decreasing with channels. Efficiency is increasing, look, because efficiency is here. So if your height of channel is increasing, efficiency is increasing. This is for nanofluid, right? It's not for water. Before I show you water, that's why look to these values. It looks lower than water. That's what I found. And I was not afraid from the reviewers of international journals. Because if you send a journal and you are from Algeria, yeah, you have to be fair. People doesn't trust you so much. They don't know me, what kind of research I did, or etc. They said, wow, these guys is really Nothing. How can he send us a paper that his research of PVT with nanofluids is very low comparatively to water? And everybody is saying that nanofluid is the best. Reject. So what I did, I sent the paper. As it is, it's not good to modify your results. This is also an advice to the young generation. Professors like me are better than me, so they know. But for the young generation, if you check everything and you find the result, look to that result, be confident in yourself, send the paper. The most important discoveries came from something that we didn't expect. If you expect something, everybody will know that. So it cannot be something original. Okay, so here I was thinking about to determine the optimal channel height. And I find something here. By combining exergy and energy efficiency, I find that there is kind of inflection point. In that inflection point, this is the optimal height of the channel, 3 something centimeters for that condition. That's perfect. It gives you the best in terms of quantity and quality, right? And I compare this method, combining, so the optimal height of the channel, we obtain this. I compared to someone the professor knows very well, Professor Adrien Bejan. He's very famous in thermodynamics, and he's very famous for optimizations of, so he's always working. He has even a non-dimensional number with his name, Bejan number, right? So the difference is about 1%. Just using the equation of Bejan to find optimal height and the proposed method of inflection. So this is my conclusion, actually. I said the water dioxide of titanium nanofluid-based hybrid collector has no, at least this is what I found, has no substantial advantage over the one based on water. And everybody, even one of the reviewer, I sent it to Solar Energy, said, no, it's very uncommon. I said, okay, so I repeat to him, so once I have to answer the reviewers, so to him, of course, so based on my result, please, if you found any contradiction or something, you just reject it, finish. I cannot say anything, that's what I found. Next, so that's what I said, I don't follow the trends. That's my career. I don't say this is the best career if we compare, but that's my own way. I don't follow trends. I set just my own goal and go for the extreme. I do my best. Okay? So. Then I propose something new also, a spherical solar water heater. So generally, this is also something interesting because in solar energy, as you know, solar is not sitting the whole day in the same position. Therefore, your efficiency is not the same the whole day, right? So the idea is sometimes that if you have spherical surface, so every day or every time there is some part of your collector that has receiving electromagnetic energy from the sun. But generally what they did, because this idea exists already, they separate, they separate the collector or how to say, the tank that you have to store your thermal energy from the, but for my case, to reduce the volume, etc., I said, why not putting inside this? So generally they use spherical one, right? They use the spherical one. for my case, I said probably there is kind of optimal geometry for the tank that could store the energy more efficiently. So I could propose this kind of three. So they have same volume, right? This sphere and the cylindrical one. This is the conical one. So we compare this, and what we found actually, so the circular truncated one, we found that this is temperature distribution inside the tanks. Look, spherical one, everyone thinks that the best form of geometry for storing the thermal energy is spherical. Yes, this is in terms of quantity. But in terms of quality, if the water is mixing, this destroyed what we call the thermocline. So in terms of quality, it's not good. And here we see that the majority of the volume has the same temperature. Means there is a mixing between the fluids. Here, no. Look. So the conical one and the cylindrical one are better. So this is time, okay? This is for 600 seconds, and this is for the double, 1,200. So that's, I'm using some, how to say, non-dimensional number to compare between this storage tank. So we can see here that the best is the truncated cone. Then the spherical at the beginning. And then very quickly, the spherical one lost the quality of the storage energy. The cylindrical one keeps its maximum as long as possible. So if you are using such equipment of solar energy and you want it to be used for a long period of time, it's better to use it spherical with cylindrical one. But the best, if we compare in terms of efficiency and quality, is the conical one. So I tried to make a patent also about this, but they're not yet. So this is Richardson number to compare between the. So I arrived to something very interesting. Maybe also I like to make a little bit time. So one day I was invited by one of the biggest company in oil in the world, the Algerian company. But because of her, this company, we are eating bread, after we said, because a lot of billions of money is coming from, as you know, oils and natural gas. And they invited me to make a research proposal. Good. So I was happy. So there is a very interesting topic. This topic can bring billions of dollars to our company, not millions. The enhanced oil recovery project. I will explain to you. So, oils, what we can extract, is not everything. The oil has high viscosity, so it's stuck on the rock, deep inside. And with our technology, we cannot extract such petrol or oils. And sometimes the quantity that we cannot really extract is around 60% of the whole reservoir. So you just extract like 40%. So that's what I mean. The recovery rate is the percentage of recoverable oil compared to the total amount initially in place. The example of this site called Hassin Saoud, one of the biggest in the world, very famous. Imagine since the French occupied Algeria, they discovered Hassin Saoud, and until today we still extract oil from it. So the amount is huge. So Hassin Saoud, but if I can, for example, propose to them technology to, how to say, recover 1% only. 1%, it's $500 million barrels of recoverable oil, which is equivalent to like they discovered the new field. Okay, so this is what I proposed to them. This is very important. I propose what we call a thermal enhanced oil recovery project. Thermal recovery is successful technique. Why? Because it involves actually burning natural gas. So in this, for example, region, they have natural gas. They burn it to make vapor, right? And then you inject such vapor inside because it's hot and vapor can go everywhere, not like liquids. So it warms the oil, reduce viscosity, then you can extract the oil. That's the idea. So natural gas to produce steam, which is injected into the reservoir to heat the heavy oil and reduce its viscosity. So this is the idea. So the main objective, as I said, is to heat the oil underground, okay, and to reduce viscosity. What happens? So I explained to you. Look, this is oil, and you will, for example, this is water. Generally, what they did, because this project exists, for example, in the United States of America, they use gas. So natural gas, you burn hot water, very high pressure. So this could be also a topic that could be interesting for example, people in your lab, because they are working on high pressure, etc. Because here high pressure is very important to model things. So then you put steam, inject inside. This is oil. So in these areas, oil is viscosity is too hot. So you reduce this, and of course you can extract, I don't know how many million of barrels. So that's very important. So my idea is like this. Instead of using natural gas, I will use something that is in competition with conventional energy, solar. People, they always think that solar is in competition with conventional energy. For me, they can collaborate anyway. So we use this technology to warm up the water, generating vapor, and then injecting such vapor inside. So that's the cylindrical panels. And what is interesting in Hassan Saud also, be careful, because if I talk about such application, location is very important. Why? If you don't have water, no way, specific. But in that region, there is even an ocean and the ground in Hassan Saud. So there is water, so no problem. So the solar technology use like the technology of greenhouse. Why? Because the south, I don't know if one of you have already visited any Sahara, not only Algerian, I mean, sometimes. You have dust. So this will destroy and also reduce the efficiency of your panels. This is problematic. So the idea is using greenhouse to protect them. Okay, look, like this. This is a map of Algeria. And what is important in this technology of the concentrated solar, you need what we call a direct incident radiation high. And Hassan Saud is exactly here. So this is very good for application for this concentrated. But here, for example, no. Like the shaft, like the wake. This he actually he's coming from here. I show you where from here. And her, she's coming from almost here, the border with Tunisia. And I am from here, a little bit with the green. Anyway, so I said that Hassan Saud is here. So in terms of potential, because you are proposing to our big company to put a lot of money to make a very big, for example, area to generate the vapor. So you need water, and you need that your direct radiation is high for such technology. And this is perfect. So I showed this to Sonatrach. I said, because Sonatrach, they have other oils somewhere. It's not working there. But here, for that, Hassim Saud, very good, no problem. Anyway, that's what I need. Greenhouse, it looks like this by artificial intelligence. So this is, you protect from sand. Because we have sand, etc., so it will destroy efficiency. So I make this presentation in front of very experimental panels, and they were very satisfied. So what they did, suspense, like in the movies. As I said, sand. Actually, they give me something. I'm here, and this is, this guy is old, so has very high position in our company. And finally, I was happy at the end, but just a certificate of recognition, but no financial support. Unfortunately, that's what happened. So research, sometimes you can propose very good ideas, but it's not always that everyone can help you. The system of financial, for example, if I were in America, it's different. There is one guy from Algeria. He's very famous. He used to be the chairman of National Institute of Health. So he did his, research in the United States. At first, he went to France. And then that guy, he's doctor. His name is Zerhouni, Ilyas Zerhouni, very famous for, he discovered some system for electromagnetic to make some checking of concerts early, yes. So he went first to France, and then he gets some idea and said to his supervisor, Prof, I want to do this. That guy answered him, why you want to do that? He said, at that time, I understand that I cannot stay. He left to America. And the first meeting with his supervisor, he tell him the idea. He said, why not? So that makes the difference between the United States and the other countries. So here, no way. So as I said, there is a kind of paradox that we can use solar energy to increase the conventional energy oils in Algeria. It's possible, of course, sometimes to combine the two forms of energy. They are not really, in my opinion, really in competition. If you can solve the problems of pollution, that's perfect. So now I return to my first slide, the doors. I started my career by looking to different ways to follow. And the conclusion of this journey is I cannot open every door. One door is a little bit, one is completely open, I solved the problems, no problem. Okay, like thermal conductivity, nanostructures, perfect. Others, little bit, and some no. So why? That's the conclusion of my research. We need collaboration, and that's why I'm here. I came to this university not only to see this your beautiful country in Portugal, but also to make some contribution. Okay, to work together, if possible, of course. So that's the way. So no one can make good research alone. No one. Pluridisciplinary research group is mandatory. It's not an option. International collaboration, it leads to what? addressing global challenge through united efforts, enhancing academic quality and reputation, visibility of your research, and so on. Cultural exchange, coming from different cultural backgrounds to Portugal, and building international networks, and broadening research horizon and resources. And finally, if I allow myself to give you advice, never give up. You just try, always keeping trying, maybe. So now I give you.
Thank you, Prof.